So hi everyone, thanks for joining us today. Okay, so today, as you know, we are having a talk on stellar types evolution and spectroscopy. So now I'll just give a quick introduction before the talk actually starts. Okay, so this is the timeline for today's talk. First, we have the talk on stellar types and evolution. Okay, I see a typo here. Sorry, guys. Okay, so the first part will be by Mr. Tan, and then the second part will be a talk on stellar spectroscopy and citizen science by Mr. Singh. And then after that, we'll proceed on to the Kahoot quiz, and some of you can win some prizes. Then finally, we have the Q&A. So now I'll share some information about our speakers. So Mr. Tan is a science educator at Science Centre Singapore, and he specializes in astronomy and physical science content. And then we have Mr. Seng, who is a manager of exhibitions at Science Centre Singapore, and he specializes in astronomical spectroscopy. So now, without further ado, let me hand over the time to Mr. Tan.
Thank you, Mirabel. Hi everyone. So I'm Mr. Tan. You can call me Ji Hang. That's fine. So I work with the Science Centre Singapore, and a pleasure to be invited to kind of give a talk for one of the session along with Mr. Seng. So Mr. Seng also is from Science Centre Singapore. He's actually just joined quite recently, and he does a lot of very cool things. And I think you all can see one of his scopes in his background already. Yeah. Okay, I don't have my background is my room, and yeah, there's no scopes, unfortunately. Okay. So working in the science center, right? We do science communication, and to be honest, my depth of knowledge on astronomy is not as I would say astronomical as you I hope, especially if like any of you might be doing physics related modules or astrophysics related module. So I'll keep it to a very simple level, such that a general public can at least have a brief understanding of the different types of stars and also how stars evolve. All right, so I'll just bring up my slides first. Oops. Okay. And I'll just bring up the video panel. Oh yeah, I forgot to mention. Really sorry, everybody. Yeah, there's a reason why this talk was suddenly become online, and the reason is because of me. Yeah, I'm really sorry about that. But nonetheless, okay. I hope through this you all can get more interested. I think I also see some familiar names. Maybe I think this might be the people I really know. Okay. Anyways, so stellar evolution. So stars, they evolve. Okay, they evolve. Yeah, they evolve. I wouldn't say they evolve like Pokemon, or like Digimon, but yeah, they go through stages. And actually, scientists, they find out this evolution through modeling and also through observation of all the stars. But I think before we go through, before we start, right, I just want to kind of set this kind of tone first. And every time we talk about astronomical things, when it comes to the context of time and distance, right, it's very different. So when you talk about stars, right, you talk about stars being formed, stars going through their different stages of life. Okay, we talk about millions and billions of years. Okay, whereas for humans, we live only for a century at most, and like our observations or recorded observations of the night sky, it's probably just a few thousand years at most. Okay, and that is actually still, in a sense, not sufficient to have a sort of visual observation of through all the stages of stars. So the best the scientists can do is through models, through math, and through observing as much as possible. All right. So for the universe, for the space, right, you can think about the universe like a world. And if let's say the universe is like a world, right, then galaxies will be sort of like countries. Okay, and in each countries, right, there'll be the individual citizens, right, and the citizens for the galaxies are actually the stars. Okay, so stars, right, they come in a lot of different characteristics. I can't really say shapes and sizes. Okay, they are mostly spherical in shape. Yeah, I hope my video panel is not blocking you also, by the way. Okay, yeah, it's better. Right, so they also range in sizes. Okay, size from about 20 kilometers to 20 solar radii. Solar radii basically means the radius of the sun, which is around oh, I can't remember the number, but I'll look up on that later. But we compare it to the size of our sun in our solar system, right? So to 20 times of that. So if you kind of, if you don't have an idea how big 20 solar radii is, you can kind of imagine extending from the sun to the orbit of around Jupiter. Okay, that's the size of like one of the few largest stars that we can observe. Okay, and stars are mostly spherical. In fact, some of the most spherical or most perfectly spherical objects in nature are actually stars because gravity, right? And then again, stars, they can range from a few million years to a few trillion years. And later we'll kind of explain how is it related to the mass of the stars, right? So the mass of the star actually determines the fate of the star quite a lot, okay? And also stars, right? They are mostly made of hydrogen. Okay, and along the way we also discuss about uh, stars. Okay, how are they like the sort of factories that will produce the so-called heavier elements in the whole universe? Because I won't go through in that, but if you kind of read out about the Big Bang and how about the first few seconds of life of the universe and all, then you realize that actually most of the first few matter that's created, right, is actually mostly just hydrogen and helium. But then, as we know, being on Earth, okay, we have elements that's heavier than hydrogen and helium. So the best guess that where all these heavier elements come from is really through stars, and we kind of see how they come about. Okay, so right, stars, they're like people. They come in a lot of different characteristics. Okay, so right, let's take a look at this first. So the birth of a star. So you just first kind of go through a little bit about how stars are formed, right? The birth of a star. So right, like people that have to go through some process to to be born. So on the left, right, okay, you see this ball of what do you call that? uh Red ball. Okay, you can think of it like a plasma ball, right? But this is actually just a computer simulation of potentially how stars actually form from a big gas of molecular clouds in space. So in space, right, there are all these big gases of clouds. Okay, on the right you see Orion Nebula. That is one of the classic example. So I'm not too sure if you had already went through your physical observation session. I think some of you came to the Science Center Observatory the other time. So hopefully, I think on that night, you all managed to see the Orion Nebula, because I recall that evening the weather was not very good. Okay, but I think through the session, some of you might have heard that the Orion Nebula is a stellar nursery where stars are being born. That's why we use it as an example. Okay, I'll go through a little bit more. Right, so this big gas of clouds in space, right? Okay, they're really, really big. We use light years to quantify it. So 1 light year is like the time that, sorry, the distance that light would travel in a year. And usually when you talk about these gas clouds, okay, they can stretch from a few light years to maybe 100 light years on. All right, so on the left, right, this video that I've got online, okay, from the University of Lancaster. Basically, the scientists they model this big of gas of cloud. Okay, you just start with a ball first, okay, and you observe the process of how the gas collapse, because they put in the parameters of how like gravity works and so forth. Okay, and you see because of gravity, right, the clouds will start to clump together because gravity is an attractive force. Okay, but later along the way, right, just watch what happens. Okay, at certain parts of the clouds where the clumps, okay, becomes too dense, right? So the color indicates the density. Okay, although it's logarithmic, you can think of it as the brighter it is, the more dense the cloud is, right? So just watch this first. Okay, and just take note of the dimensions on the top left and also the year. Okay, again, you see, we talk about astronomical years. Okay, it's really like 10,000 billions and millions of years. All right, so they will pause here first. Okay, but I think you see there's some parts that are already what I call that, getting clumped up with more gas. Okay, and if you're wondering what are these gas mostly made of, again, they're mostly made of hydrogen. All right, so you see here, there is some spinning going on, and you see all these dots being formed. And yes, those are stars. Okay, but to be more specific, we call them protostars, meaning stars that are just being born. Because you realize that stars, they go through different stages of life, right? So the earlier stage, we call them like protostars. Okay, and you see some of it get swung out. Okay, and I kind of hope you kind of do observe that, you know, these stars, they form in like a cluster, in a bunch like this, okay? And some of them, they will actually get bounded together in groups of mostly twos, okay? And you form what we call a binary system. Okay, I think that's it. Okay, all right, so basically that's a model simulation of um, how stars are formed, right? In a big gas cloud. Okay, and see that they tend to form in a group, right? And of course, with all the different interactions, some will get spun out further. Okay, some will kind of get gravitationally bound together, right? And turns out actually quite true, right? In fact, most of the stars in our night sky that we see, right, they're actually binaries, meaning that they form two, some even more than that, right? Some could be visual binary, meaning they just appear to be close, okay? But scientists, they did the math and everything, okay, and they realized that actually most of these stars, right, they have to be binaries. In fact, I think there was a rough estimation somewhere. Uh, I cannot really remember what's the exact estimation, but I think, I guess it could be around two of the stars are binary. I guess that kind of makes sense also, because I mean they're in twos, so two-third, I guess. Then the one third are the lone star. Oh my god, so sad. Okay. Anyways, all right. So stars do form in clusters. If you have the opportunity again for the next observation, okay, you might also observe some star clusters. There's actually quite a lot of star clusters in our night sky. I think Pleiades is one of them. You might have also observed that, right? So this process, right, it takes like 10,000s of years and millions of years, right? So we can't exactly see, you know, stars being formed in a way like the simulation, right? But in the Orion's Nebula, okay, we can get close to it by looking at what we call this thing called prodips, right? Basically, it's just stars in the early stages of forming. And in all these like very high resolution images of the Orion Nebula, right, they actually detected some of all these like prolapse, if that's how it's pronounced, or like protostars, okay, being formed. And basically, you can see that they actually have this like matter around it. Usually, it's accretion disk. Basically, the remaining lump of gas, right, that was kind of falling in, but they didn't sort of make it to the center portion, which will form the stars, right? So depending on the conditions, right, if the condition is good, the disk form, it's a very nice disk. Okay, there's a good chance that planets will form. Okay, and in fact, one way to see if planets form, right, or if there's exoplanets, is actually through spectroscopy, which is a topic that Mr. will cover later. Okay, and if let's say it's very turbulent, then there's a good chance that it might not have what we call it, planets being formed, or planet simmers. There's a term for it, for like these potential planets being formed. And I think one of the examples is like this and this as well. Yeah, so these are the places where stars are formed, right? These gas clouds. And these gas clouds, in general, we call them nebulas, but they're different types. And this one in particular, the Orion Nebula, where, you know, it's an active star forming region, or where a region or stellar nursery, there are a lot of young stars. All right, we call it, this one in particular, we call it emission nebula. All right. Okay, so wow, talk a lot about the birth of a star, but okay, the main topic is still the birth, sorry, the stages or the life stages that a star will go through. Okay, so before that, right, we need to kind of go through this as well, because uh, we need to kind of classify the stars. And one way to classify the stars is through this system here. Okay, it's known as the Morgan Keenan classification. All right, and basically it went through a lot of changes, but in general, there's three of these labels. right? The first label is this alphabets. Okay, it came from this Harvard spectral classification, and it starts with O and goes through B, A, F, G, K, M until S. But usually you only usually see the first 7 letters from O to M. O is, if I recall correctly, should be the hottest, and then M should be the coolest star. But it's not as simple as kind of like talking about the temperature of the star. Okay, it's also by the spectral line as well. Okay, and then the I and S, right? I and S. Okay, the I and N is actually for a special type of star called carbon star, and S is for another kind of special star also that is similar to M stars as well. Okay, then also the second spectral number, it ranges from 0 to 9. Again, it's just a subdivision of the main Harvard spectral classification. I call again, it's by the so-called surface temperature. I can't remember if 0 is the hottest, 9 is the hottest. I'll check again later. But yeah, 0 to 9. I think 0 being the hottest and 9 being the coolest. And finally, the luminosity class. That one has that one also depends on the spectral lines of the stars as well, and it is labeled from the Roman numerals from 1 to 5. Sorry, yeah. But we don't need to go through this in detail for now. But I think it's just good to know for this. And this classification, right, also can tell us a little bit more about the stars, and also quite one interesting thing is also the colors of the star, right? Because the colors of the stars, right, will actually give us a hint, a very good hint about the surface temperature of the stars, and also to the mass of the stars as well. Right. So as an example, our sun is actually a G2b. So you can G is somewhere on the cooler side. Okay. And it's kind of hot in the sense of the G inside the G class of stars. Okay, and 5, which I cannot recall at the moment. What does it mean? So maybe I'll try that again later. All right. So on the right, there's this picture that I'm showing you. Okay. All right, and just a moment. Okay, and you can see I'm just giving you the example on Orion's constellation. So the constellation of Orion. Here you can see Betelgeuse M2I, M21, sorry, right, just B8I or B81. Okay, and this is actually, oh yeah, I kind of forgot to mention this. So what you're seeing now is not like a bad image taken of the Orion constellation of Orion, but instead it is actually what we call a defocus image. Okay, a trail defocus image. So when you do this, right, you actually bring out the colors of the stars more nicely, so you can actually observe the colors. Okay, and also on the left, I also included this chart lah of the different classes, the Harvard classes. You can see O to M, and basically the temperature range is shown as well, right? And you can see O is the hottest, and M is the so-called the coolest lah. And but the thing is, more importantly, is actually the spectral lines. Okay, the spectral lines of the stars that determines the class. And other astronomers, they actually use spectroscopes, right, attached to the telescopes to kind of study this, and it gives a lot of very important information. And Mr. Song will actually cover a little bit more about this in his presentation. Okay, but these spectral lines, right, okay, give us a lot of information, including the composition of the stars, right? So although the star is mostly made of hydrogen, okay, it can also contain other elements as well. And stars, right, we also have sort of this a way of calling them first generation stars and the second generation stars. So the second generation stars are also called the stars, right? They actually have heavier elements in them, although they can be young, right? So basically, the earliest, what do you call it? The earliest stars, right? Especially the so-called more massive one, because the more massive one, right? They actually are hotter. They actually burn faster, and they also die younger. Yeah, kind of a bit of a like here for a good time, not for a long time. Yeah. So in this case, right, this massive star, they also go through more stages of nuclear fusion, right? And then what it does is that it will create more of these heavier elements, and when it dies later, which we'll cover, okay, how like the way it dies, right, it actually can sort of shoot out or deposit heavier elements that it has created through nuclear fusion in its body, right, out into space, and where second generation stars or like say gas clouds nearby will have all these heavier elements, and then they again can go through the process of stellar formation. Right. Okay. So again, spectral lines. With the spectral lines, right, you can also sort of measure the movement of stars. Okay, be it its velocity of stuff. Okay, its temperature as well. Okay, the surface temperature. Okay, by looking at its peak, because there's some sort of science or thermodynamics behind it. Basically, there's this thing called the uh, what's the curve called? Black body curve, right? Yeah, black body curve. So basically, the black body curve will tell you the peak of where most of the so-called light is coming out, right? The peak, right, will actually tell you the temperature of the surface of the star. Yeah, and density, and also the interactions with other objects. Okay, this interaction with other objects also give clue to, maybe there might be a potential exoplanet, right, from the star as well. Okay, so spectral lines give a lot of clues, right, to a star. Okay, and also to its nearby objects as well lah. Okay, so this the I think the main idea that I think you all should have at this moment for this kind of like introductory talk on, like, stellar formation and also star types. Right. So on the left, it's what we call a Hertzsprung Russell diagram, or HR diagram in short. I hope I pronounced it correctly. Yeah, but it basically tells you the stars, right, and their relationship in their so-called temperature and also their luminosity, basically the energy that they give out. So it's a bit complicated at the moment, but for the x-axis, right, where you see the spectral class, okay, that tells us in some sense, right, the temperature of the star. Okay, you can see also the color as well. The red color parts are so-called the cooler stars, right, and the blue parts are the hotter parts, or the hotter temperatures. Okay, so this is also related to the black body curve. So basically, hotter objects, right, they actually give out light in a sense, visually to our eyes, right, they'll be more towards the white and the blue side. Whereas, like, say, cooler things, okay, then will be on the red and orange side. Okay, it's like flames as well. Flames, if you ever do kind of read about the temperature of flames, right, the red flames are sort of the cooler flames, while the blue are the hotter flames. Okay, and then the y-axis is the absolute magnitude, in the sense the brightness of the stars. Okay, and then we from there we kind of bring a relation to the luminosity of the star, which is the energy that the star gives out. All right, but I think because I kind of took a bit of time, right, I think. But yeah, so I won't go through this too much on this, but okay, we'll come to this diagram again a little bit later. Okay, and you can see that there are like the so-called different sections, okay, and the different types of stars. Okay, I'll again along the way explain to you like when needed. Okay, what does all these means, like supergiants, giants, subgiants, their main sequence, and the white dwarfs. Okay, and the main gist from all this, right, what I said just about like 5-10 minutes ago, is that hotter stars, they will burn faster. Okay, and in a sense they also die faster. Okay, but at the same time, right, because they burn faster, right, they also give out a lot more energy. They'll be a lot brighter. So there's this that table over here, right? You can see basically you see there is a inverse relationship between the mass of the star, okay, and also its lifespan, or its life expectancy. So the more massive the star, you can see the shorter it lives. Okay, whereas the really, really smaller stars, right, we sometimes call them the red dwarfs. Okay, they can live billions and billions of years. For context and comparison, the universe is estimated to be around 13.8 billion years old only. Yeah, and you can see like most of the smaller and the dimmer stars, right, they're actually still in what we call the main sequence stage, meaning they are still on the stable and just gone through kind of puberty kind of stage, and just be on like the this period for a very long time. Okay, all right. So with that in mind, right, all the star types, okay, and about the main idea where brighter stars, the massive stars, they will burn brighter, they'll be bigger and they die faster. Okay, whereas the smaller stars, they are less massive stars, right, they will burn longer lah. But at the same time, they are not as not in the sense, not as energetic in the sense of the energy that they make. Right. So basically, over here, okay, this chart I got it from Wikipedia, but I use this also because it summarizes the different stellar evolution quite most briefly and easiest to understand. Okay, because if you do read up on how stars evolve, right, there's a lot of what I call that not say special cases but sub cases. Okay, so the most simplest way to tackle this is to consider a massive star, which are generally eight solar mass and above. Okay, and the so-called average and low mass star, which is around 8 solar mass and below. Right, so our sun actually is considered an average star. Yeah. Okay, you can see the main sequence, that's like the main stage of life, and then the red supergiant, the red giant, it's the so-called old stage of life. It's like, it's getting old, it's gonna die soon. And then after that, it's death. Okay, you can see a lot of supernova. Okay, and we'll kind of briefly touch on that. And then the remnant, so it's what is left behind in a supernova. Okay, so we talk about the massive star first, that there are usually 8 solar mass and above. Okay, so this massive star, right? Okay, they will go through fusion first, right? Nuclear fusion. So stars at the core, because that is where it's most dense and most hot. Okay, not necessarily the most hot, I think, but that's the region where the conditions is right for nuclear fusion, whereby hydrogen atoms, they will fuse together to become helium. The nuclear physics involved is a lot more rigorous. So for now, I'll just in general just term it as nuclear fusion. Okay, but there's a lot more details. So if there's any physics students, you will have learned like the neutron capture process, the R process, all this for the helium elements. Yeah, but we're not talking about that. Okay, so just nuclear fusion in general. So for the massive star, right? So what happens is usually the core, okay, will still be always at sort of correct conditions for nuclear fusion to go on. So after the first sort of, or rather, let's think of it, the core will start with all hydrogen. So after all the hydrogen has been fused at the core, right, the surrounding area, which is mostly hydrogen, okay, will actually kind of collapse, because the core, right, will actually sort of shrink a little bit, can say condense a little bit after the hydrogen is running out. And then you shrink a bit to become smaller, and even pressure will go higher. And that process actually makes it hotter as well. And the core itself will continue to the next stage of burning. And the surrounding will also will then start fusion as well. So this process will keep going on, right, until there's this kind of onion layer kind of idea for the core. So for massive stars like this, right, you keep fusing, right? The core will just keep fusing to heavier elements until it reaches iron. So how do I put this? Okay, I think it's best to just compare it to chemical reactions. But this is quite different. These are actually nuclear reactions. But that is similar. Basically, when the reaction pathway, it's in what I call it, not feasible, meaning that it takes in more energy, right, to do the process than to kind of continue the process than the energy that's given out by the process. So sort of like endothermic process, right? So basically, you stop at iron, and when basically no more fusion can go on, right, this whole core will start to collapse. Okay, and before that, you will actually be in the so-called supergiant phase. And this happens because when the nuclear fusion and the center kind of is running out of energy, or running out of the material to continue with the nuclear fusion process. Okay, there's a disturb to its equilibrium. So the outer layers of hydrogen, right, of the star, okay, will actually start to puff out, because it's at the center of the core, right, where the nuclear fusion stop. Okay, the core will actually start to collapse upon itself. There's no more of this so-called radiation pressure to balance gravity, right? The core will collapse because of gravity, right? And then there's no more radiation pressure from the nuclear fusion to balance this movement or process out. And as a result, right, the the outer parts, right, actually start to puff up. Okay, when it comes to the older stages, okay, of the so-called more massive star. Right, so when it comes to the point where really no more nuclear fusion process can go on, right, the core collapse all the way, okay, and it's a very fast process, and it releases a lot of energy, and that will become like a type 2 supernova. Okay, and the type of supernova, right, okay, will actually release a lot of energy. And what I learned from Mr. Sung today also is that actually it's a lot more common than we think. Although I thought it wasn't that common, but it's actually observable, and there's actually amateur astronomers that keep look out in the night sky, and they will actually once in a while find like a region of sky, right, where suddenly a new sort of star-like object that popped out. But that's actually a type 2, usually a supernova. Okay, later we'll talk about type 1, but for now, for massive star, they will usually end up in a type 2 supernova, and they will fling out a lot of the materials, right, especially the heavier elements, okay, into the surrounding region of space. And then you give this kind of supernova remnant. Okay, this example here is actually a Crab nebula. Okay, it's in the constellation of Cancer, if I recall correctly. Not really visible now. Okay, but then at the end, right, you will have a remnant core, because the core collapsed, okay, due to gravity, and basically there is nothing to stop it. Okay, you either end up as a black hole or a neutron star. Right, so we'll talk about the neutron star first. So basically, in the collapse process, okay, the protons and electrons can actually fuse because of gravity, and like all this matter is being compact together. Right, so until when it's all neutron, we call it a neutron star. Right, and then you end up having some sort of pulsar. Okay, but we're not talking about pulsar for today. So this neutron star is one of the densest matter that we can see or observe in or rather in the known universe, right? But there's also a special case whereby if let's say the core is really so heavy, about estimated more than 40 solar masses. Okay, this number, it's still not really well known yet, but estimate. But this basically, if it hits this threshold, which we call the neutron degeneracy, basically when imagine you have the core as a whole ball of a neutron like this, but the weight is still so, not the weight, the mass is still so much, right, that it continues to collapse. Okay, then all known physics is broken and you get a black hole. All right, so that's at least the theoretical approach, right, to the formation of a black hole. Yes, so that is the stellar formation of a high mass star and the two possible fates, basically a neutron star and a black hole. Okay, and wait, maybe I'm still on time, right? I'm taking too much time already.
Like around 5 to 10 more minutes.
Okay, all right. Okay, so okay, but over here, right, just to go through the HR diagram. I think just to kind of have this appreciation. But basically, right, for a star like this, we'll put it in a HR diagram that looks like this. So you can take the example of the 10 solar mass star. Okay, you go through the process in the main sequence where it keeps burning hydrogen into helium, okay, or fusing hydrogen helium. And after that, when the first hydrogen runs out in the core, okay, you start burning helium, and you see that it goes into this supergiant phase. Okay, and then there's more complex or other kind of fusion going on in the core when the conditions right, and see that you end up around this region, which is called the supergiant. The supergiant area in the HR diagram. All right, so this is a high mass star. Okay, then the low mass stars, right, about 8 solar mass and below, right, they have a very different fate. So for low mass stars, okay, very different from the massive star because they usually end their fusing at the core at maybe carbon helium, right? But same thing again. So when the core is running off hydrogen to kind of fuse, right? And then the core is mostly helium already. So at some point it will actually stop fusing at the core, right? And again the core will kind of collapse a little bit, but the collapse again converts gravitational energy to other forms of energy like heat and everything, and it actually cause the surrounding hydrogen layer, okay, like this surrounding hydrogen area, right, to continue to fuse, right, because it sort of hits this surrounding hydrogen envelope up. And as a result, right, this hydrogen envelope around it will begin fusing right, into helium. And this process suddenly releases a lot of energy, and it makes it path into a red giant. Okay, and usually, right, because it's not as massive, you just stop around at most, the core might continue with helium fusing through a slightly different process to form a carbon core, right? But usually what happens is, all right, the red giant, okay, at some point will not be able to fuse anymore. Basically, the envelope of hydrogen around it will stop fusing as well into helium, and then the outer layers, okay, they will just path into surrounding space, right? Because the star kind of die already, right? And the outer layers of all the star will just puff the materials out, and you end up something like a planetary nebula. This in particular, I'm not too sure if this is the ring nebula. It could be another nebula, but these are examples of planetary nebula. Through a telescope in the past, astronomers thought they look like planets, so they are called planetary nebula. Okay, but these are pretty cool. But the so-called circular nature of this kind of planetary nebula does really reflect that, you know, when a red giant comes to the end stage of life, right, the external material just expelled off. Okay, but you see different colors in between because, right, at the core, usually of the planetary nebula, the remains of the core could be a carbon core, right? It's actually a white dwarf, whereby it will just slowly cool. But the cooling process is really, really low. Sorry, not low, really, really slow. So it takes a long time, okay, until it forms something called a black dwarf, whereby it cools to near 0 Kelvin already, right, where it already loses most of the energy, right? But as it's cooling, it actually releases a lot of radiation, and that actually kind of excites the gas around it. So you get these different colors of the planetary nebula. Right, so there's a special case. Recall that in the earlier part we talk about the birth of stars, a lot of stars are actually formed in binaries in pairs. So if there's a special case whereby the remaining white dwarf, okay, is close to a second star, right, sometimes it will actually gravitationally attract, right, the materials from the surrounding star, okay, and you actually gain more mass. And if let's say the core, the white dwarf, gains a mass more than 1.44 solar mass, okay, which we call the Chandrasekhar limit, okay, you actually go through something called a type 1a supernova. So a very interesting feature, because this type of supernova, right, they actually explode or kind of like give out usually the same amount of energy, and they are like standard candles, right, for the universe. Okay, but if let's say it doesn't kind of increase above the limit of 1.44 solar mass, you just kind of like expel all this material from the neighboring star, and you just get a nova, something like this. Yes, and that's the sort of end state for low mass stars, really. And that's also the possible fate of our sun, okay, which you most likely end up as a white dwarf. Okay, and last but not least, there's this special class of sort of stars. They are called the brown dwarf. So basically, they are like really, really very not massive stars, low mass stars, that they do not have enough mass to kickstart nuclear fusion. And as a result, they just lump as a ball of gas. Yeah, sort of similar to Jupiter, but there is a rigorous um, definition for a brown dwarf, which I could recall for now. So for now, Jupiter is not considered a brown dwarf, but there's some articles that sort of debate whether, you know, Jupiter is like a twin or like a binary twin of the sun, yeah, because of its massive size. All right, so that is the stellar evolution, and we actually come to the end. Not hold too long. Okay, I'll come to the additional resources if there's time now. But for now, yeah, that's all for the stellar evolution. Okay, there's a lot. I don't think I actually went through in. I might have missed out a lot of things, and it might be a bit confusing here and there. So later in the Q&A, if you need anything, you can just ask there. Yeah, but for now, I'll pass the time to Mr. Sung.
Thank you. Mirabel, I should begin, is it? Share my slides.
Yes.
What time should I stop?
We can stop around 9 to 9:10.
Okay, I'll take about half an hour. Keep it within half an hour. Q&A should be more fun, I think. Okay, can you see my slides?
Yes, can see.
Okay, shall begin. Hello, please call me SK, just the initials SK. I think I just joined Science Center last year, and I've been doing astronomy outreach for the past about 5 years in Hong Kong. And so my background is actually aviation and architecture and amateur astronomy. So the only thing with common with astrophysics is the letter A. Then when I started spectroscopy, amateur spectroscopy, then I tried to do outreach with it as well. I found that it is quite hard to get people excited or interested compared to when you show nebula or planets. So it was quite hard. It wasn't very successful outreach. But since tonight is a astronomy club, it's not a public, so I think this could be an appropriate topic because everybody here is probably has already a certain starting point in astronomy. So just a very brief run through within this half an hour. I'll just be brief and probably touch on many a more diverse set of topics, and then I think it's better that way than if there's anything that piques your interest, you can go deeper into it. So it's more of a broad overview rather than something in detail. As you know, photometry will be monitoring the brightness of stars, and this is what the AAVSO, the American Association of Variable Star Observers, they do very well. They have data stretching back more than 100 years, and they have lots of data on light curves. Many researchers actually use their data for their papers. And the other one is, of course, astrometry, which is measuring the position of stars accurately. And then you have spectroscopy. Most of what we know about the universe actually comes from spectroscopy. Not downplaying the importance of the other ways of studying light and stars, but because spectroscopy gives you a lot of details, as Ji-Yang has mentioned earlier. For example, in this case, this is the light curve of R Scuti. It's a kind of star called RV Tauri type. It's not the perfect simple example to use because RV Tauri stars are a little bit complex. Not fully understood why their variation is a little bit chaotic, but we just use it to show the light curve versus spectroscopy will show you at this point, at this the dimmest part, what is the star doing? It's actually becoming like a M star spectrum, but it brightens, it goes through the spectral class, and then it changes to a kind of different shape that you can see with different absorption lines. So that's how much it changes, because the magnitude change is quite large for R Scuti as well. You can see it's about 3-4 magnitudes. So spectroscopy will review the details of the changes.
Sorry, I think your microphone is picking up some other sounds. Maybe like can move it a bit further.
Oh, further, is this
Yeah.
better? Is this better? Is it better this way? Or
Yeah, it's
separate?
like, yeah,
Okay.
it's better.
Okay, so maybe it was too close. Sorry about that. And okay, how is spectroscopy done? This picture shows a very quick overview that as you have seen in the earlier slide, you see the typical, this kind of absorption lines within a continuum. So this is usually normal stars, you see this kind of spectrum. And then there are some strange stars or like PNE, planetary nebula, you see emission spectra. So the reason is because when the continuum of the star from the photosphere shines to us, and then when it shines through the photosphere, the elements in the photosphere, different elements actually absorb the spectrum and then cause these absorption lines. So this is the continuum with the absorption lines. And for the emission one is the opposite. And I actually put this diagram because a lot of people, when they see the diagram for the first time, it can be confusing. Why does this cloud give you emission lines? Because usually, like what Ji-Hyung mentioned earlier, in molecular clouds, you have the ionizing source, which is hot stars. Usually you have OB stars, hot stars giving out a lot of UV radiation. So that is the source, energy source to excite the electron transition. So the electrons transit to higher levels. When they fall back, then they give out light as emission spectrum. So that's the difference between absorption and emission spectra. This is actually I added this to show what spectroscopy can do. This is actually the Lyman alpha series showing very distant QSO quasars, and it shows the up to Z equals to, I think 6 is here, and then this is the oldest time. And this is just to show you that what spectroscopy can tell us. It's actually showing the absorption from neutral hydrogen early on in the universe. So it's giving information to the cosmology. And then as more young stars are formed, they actually, the term the astronomers use is free ionization. So by about Z equals to 6, Z is the redshift, by the way. And then there's more and more stars that are born, and then they ionize the neutral hydrogen, then that part of the universe becomes more and more transparent. So this is one example of what spectroscopy can tell you. So how is spectroscopy done in the professional world and in the amateur world? Is a little bit different. In the amateur world, but the principles are overall overview principles are similar. You have these things that you want to see. They go through the ISM, interstellar medium, and it changes them in some ways, in different ways. And then it goes through Earth atmosphere, and then we pick up a lot of these molecules in Earth atmosphere. I'll show you later. And then eventually it comes to your telescope. It goes to your spectrograph. And if you're physics or chemistry majors, you probably have done diffractions and all that. Basically, you split the light like what Newton did 400 years ago, and split white light into colors. And then as you split into higher and higher resolution, you get more and more information. And then the detector detects it. So that's what we do. This is an interesting spectrum. For continuum, typical Balmer absorption, and then there's a very large emission line at the H alpha. Usually spectrum like that is like a flare star. We'll talk about flare stars later. Okay, so this is what we do, and this what can amateurs do with amateur equipment? Amateur spectroscopy is relatively new. Just before 2000, most of it is a lot of DIY, and if you have seen the forums in the online, you have seen a lot of people try to DIY astronomy spectrographs and have failed. I've tried my hand early on a little bit also, and it's not easy. So in the end, ended up buying some of these commercial spectrographs. The most common brand most of the amateurs use is this French brand called Shelyak, Shelyak. Okay, but let's start from the beginning. If you want to start on spectroscopy and you're not sure whether you can keep going, you get bored, you don't like it, and then you don't want to spend all this money to buy a spectrograph. Usually, people start with this analyzer. I have it somewhere, but yeah, it's just 1 inch. You can drop it into your eyepiece, so you can see the spectra visually, or you can put it on your camera. So it's quite easy to use. It's developed by this guy called Robin, a British guy, Robin Leadbeater. He's very active, and he's a very advanced amateur spectroscopist. He is the first amateur to be able to classify supernova. I think he has more than 20 supernova classifications now. These are advanced amateurs. They're really good. They really know what they're doing, and they're very helpful. They give a lot of advice when people start out in spectroscopy, and they are the ones helping on the forums and all that. Quite a few of them. You hear the few names coming up. And RSpec is also the first package that most of us start with, developed by Tom Field. It is the only one that you need to pay, but it's not very expensive, and it's very nice to use. So this is a good way to start wide field spectroscopy. It's not a slit spectrograph. I will explain what is a slit spectrograph later. And right now, most of us who do low res or high res this spectroscopy, we use this Christian Bou, French guy. He's the designer at Sherlock. And this software he says is free, it's very powerful. And some guys actually download IRAF, which is what the pros use. It's a Linux system. And after you get some experience with this star analyzer, they have the 100 lines per mm or 200 lines per mm. It's a very low res diffraction grating. Then you can try to do on your first slit spectrograph, which is give you resolution of 600. And then you can move on as well. Right now, I got this high resolution spectrograph last year and just beginning to have fun. At high resolution, you really see a lot of lines, and it's a lot of fun. Just a note on resolution. The pros will call this a low resolution, but for amateurs, 20,000 is really quite good already. The French guy, Christian, he has gone to like 50,000. The pros, 50,000 is medium. They do it routinely. I think the pros actually go to 200, 300,000 resolution. Okay. So this is the LP600. It gives you a resolving power 600, which is in terms of angstroms, you get a resolution of about 10. Just not quite enough to split the sodium D lines, but it's very good to begin amateur spectroscopy because it gives you the whole optical range from about 3005 but the good data is about 4000 to 7500 angstroms, which is the optical range. It gives you a very nice shape. You can see the continuum of different types of star. The hot stars are very hot they peak in the near about 4000 or 3000, and then the cooler stars. So I'll show the spectra later. And how do we do it? We do this, we place a star on the slit. Usually we use, depending on your seeing, but most of us use 23 micron slit, and then you guide on the star, keep the star there. If the star is bright, the exposures can be short, but if you go with the LP, I can reach 13 to close to 14 magnitude on a 2-hour exposure, so you need to guide on the slit. Your equipment should be able to perform the guiding into a reasonable standard. But for bright stars, no problem. When do outreach, use a color camera because it shows the color of the spectra better, and just choose the bright stars, and you can see the different absorption lines in the different type of star quite easily. In 15-20 minutes, I can go through the OBA, FG, KM, all the stars. So that's good for outreach. And this one shows the principles of the litho spectrograph for the high res, which is called the high res 3, the Seow. Let's just continue. Okay, a little bit of theory, but I think we'll browse through this very quickly. HRD, the Hertzsprung-Russell diagram, which Jiang has mentioned. This is the D-sodium lines, which I took with my LIRES high resolution, and it splits the the doublet very clearly, 5889 angstrom. This is actually for daylight. Just when I bought it, when I got it last year, then I just took just using daylight. And when I do outreach, I'll show the Fraunhofer lines. And this one is just to show you in 1924, 24 Cecilia Payne. We have to remember that astronomy is it's not a really young science, but a lot of the developments are relatively recent. So in 1924, they still thought that stars are made of materials like the planet. They thought it's the same. So when Cecilia Payne wrote her thesis, 1924, using this ionization equation, the Saha equation, and proposed that no, actually it's not. Actually, stars are made of mostly hydrogen and helium. And her supervisor actually told her to tone this down because it's ridiculous. And then now you see it's not even 100 years, but we know so much more, and we know that she was correct. A lot of astronomers call her thesis the most brilliant PhD thesis. Okay, so this shows you the OBF GKM, the stars. As we mentioned, the hot stars peak to the left. In astronomy, we always put the higher energy to the left and then the cooler ones to the right. And then, yep, 5889, this is a sodium D. So at low resolution, you cannot see the doublet. You will see this absorption line. And what do I want to say here is, after a while, you become familiar what stars have what peculiarities. Let's just mention a few. The A stars, when you just begin, A stars are very good for calibration and to identify because they are very strong in the Balmer series, which is the transitions from the n equals to 2 for the hydrogen atom. And so this is H alpha, beta, gamma, delta, and so on. And then there's you see these stars have a sudden cliff. It's called a Balmer drop. It's because above this energy, the n equals to 2, the electrons are all ionized. So all the way to visualize this is that this part is all absorbed because you have the electrons that are able to absorb the light. So all this light is gone. It's a little bit like the Lyman alpha forest that we saw earlier. So this is how we can deduce the conditions in the stars. And then this is H and K lines, which are the calcium lines. And the interesting thing is that here they have removed the tellurics. The tellurics are the water and O2 molecular lines. I have some of my spectra later. I'll show you. Okay. Yeah. Let's just.
We are hearing a lot of the interference again.
Oh, sorry.
Just now
It's
before the talk, it's okay actually.
stranger. Is it look better? I wonder why there are no vehicles at the moment.
I think like further is better.
Further this way.
Yeah.
Okay. Let me know if it's not clear anytime. Just stop me anytime. Okay. These are some of the spectra that I've taken. The O is missing because O stars are, like what Jiang said earlier, they are superstars, they are rare. So I have only a little patch of sky out of my window at the moment. And for this night, there are no O stars. So it's a B, A, F, G, K, M. The characteristics of the cooler stars is that you have molecular lines, whereas the hotter stars are too hot for molecules to form. Yeah, this is the characteristic Balmer series. And because it's superimposed here, yeah, this is the tellurics. 585856559. No, I think this is tellurics. Yep. When it's not superimposed, it'll be clearer. I'll show you another spectrum later on. This is A star. The reason why Balmer series is so prominent in the A stars is because A stars are about 10,000 degrees. So it's about the temperature where the amount of electrons actually has the energy to move to n equals to 2 state. And then when they transition from n equals to 2 state, giving you the Balmer lines. And this is I can't see, must be a carbon star. Yeah, this is a V-puff carbon star. Carbon stars give you these are raw spectra. And then after you calibrate, wavelength calibrate, this is what you see on the graph. But when you just take them off of your camera, this is a raw spectra that is not calibrated, not wavelength calibrated. By the way, calibration on the vertical axis is a relative intensity, which means no units. I haven't gone into absolute calibration yet. When another project to do is to do absolute calibration, where you calibrate in terms of flux, which is ergs per second per angstrom. Then you can do even more science with that. This is flux calibrated. Okay, this one is just to show some of the theories in the stellar evolution. And because I remember I listened to this astrophysicist Sri Nivasan's lecture on YouTube. It's very nice. I think you will like it also. And he said something that I remember. He said, we live in the sun because the heliosphere and the particles, the solar wind. I thought the picture is very nice because it gives you a perhaps more accurate picture of what the universe is like, where there are different bubbles of spheres of influence. The interstellar medium is not empty. And then bright stars have this radiative pressure, and when supernova happens, the shock waves causes the molecular clouds in the nearby region to collapse, and they influence the formation of stars. So there's a lot of interaction going on. And I think just a few weeks ago, there's a very recent paper published talking about the bubble that the solar system is in. So there's a lot of active research in this. And another important concept, if you are interested in stellar evolution, is the interiors is whether it's convective or radiative. And our star is radiative inside and then have convective shelf. The A stars, they have this, the hotter stars start to have a convective cores. The reason is because the hotter stars on the main sequence we're talking about, MS, the main sequence stars, they have convective cores because the temperature gradient in larger stars, they don't go by the PP chain, their nuclear reaction, they go by the CNO cycle, which is a steeper temperature gradient. When you have a steep temperature gradient, then you are more prone to convection. And then cool stars are purely convective. And that's very interesting because remember we talked about the flare stars earlier. then why are flare stars? They are usually the M stars and the cool stars, because the convective stars, we know that magnetism is formed by moving charges, because convective means a lot of motion of the plasma, and then it is believed that the flare stars flare because of magnetism or magnetic reconnections and all that. Of course, it's an active area of research in astronomy, astrophysics. A lot of things are, there's a lot of uncertainty in many areas. Some areas are more developed, some are less. Like the protostars, the T Tauri stars, the formation of stars from molecular clouds is much less certain and much less well known than the evolution of stars in the later stages in the MS, and then the subsequent evolution of stars. Okay, this one, Jiyoung has already mentioned some of this. I just want to expose the many, they call it in physics, you call it the particle zoo. Here you can call it the variable zoo. There's so many different types of variable stars. And if you are keen, I really highly recommend AAVSO. You don't have to be a paid member. The resources there are very good. You can contribute to data as a citizen scientist as well. I think it's a very good way to learn. I contribute my data there as well, photometric and spectroscopic as well. Okay, this one Jiyoung has also mentioned, so let's not dwell too much on this. I just want to bring your attention to Wolf Riot stars and the instability strip, okay, because we might talk a little bit more later. And yep, you see, look at the amount of classifications that there is. I was very interested in CVs, cataclysmic variables, for a while. Don't confuse the CVs with the CFIT or CFIT variables. Is a different type. But usually CVs, we call it cataclysmics. These are what Jiyoung mentioned earlier, which is it is believed they are the progenitors of the type 1a supernova, where these are very interesting objects. Why? Because they are so close, the two stars are so close together that one overflows the Roche loop. And then the one with the bigger mass, usually the white dwarf, is able to suck in material. And then once in a while, over here, the picture, the classical nova happens when there's instability in the accretion disk and it flares up. And this is where we can pick up this very interesting light curves. Almost there for time. So another important concept, some important concepts in stellar evolution is opacity, how opaque the gas or the plasma is, the photosphere. And opacity affects a lot of the properties of the stars. So remember we mentioned about why after the scientists started having more data, they plotted the HR diagram, and then they realized there's a certain strip where stars tend to vary a lot, along the instability strip. And it's explained now by this kappa mechanism, an important one. It's not the only mechanism for variability, but it's one of the more common ones, or most common ones, and one of the important ones. Can think about it as a heat engine. When the star compresses, and then what happens, and then it overshoots, and then it expands again. And the interesting thing is that opacity actually is dependent on density and temperature, but it's much more sensitive to temperature. So actually, when a star compresses, it actually heats up, and then by right you should get less opaque, and then it shouldn't be able to bounce back after it compresses. But this is explained by partial ionization. So I think I will not go too much into this, but just to you have an idea that these are some of the concepts going on in the variability of stars. So just last 5 minutes. Oh, I'm still at the spectra. Okay, these are some of the spectra. I mentioned the Wolf Riot stars. I still remember the first time I saw this kind of spectrum, because usually you see spectra like that, and then suddenly you see these two dots. And these are the very hot stars at the top left or top middle of the HR diagram. They are very massive stars that they evolve very fast, and then they have already started to lose their outer layers. So when they lose the outer layers become very diffuse. You no longer see the absorption lines. You only see the emission lines that from this diffuse circumstellar material, and then they are radiated by the hot cores the exposed cores of the stars. These are very interesting stars called Wolf Riot. And they go up to like 100, 200,000 kelvins. And then, okay, for radial velocity is blue shift, red shift, the binaries that Jiang has mentioned. What else? What other projects we can do? Measuring redshift of galaxies is a relatively easy project to do. This is the redshift of M77. You can measure M31 Andromeda as well. It's a blue shift. But if one accuracy, use the high res one, I think it gives you quite accurate. I think 200 something kilometers per second towards us. And interesting part about PNE nebula, this nebula spectra is that they have these emission lines, which we know because it's a circumstellar, right? And in the 1920s as well, people actually thought that there's this new element called nebulum. They call it because it's from nebula. Why? Because these emission lines don't fit any of the known data. And people, it doesn't fit the hydrogen, it doesn't fit the nitrogen, it doesn't fit. So these are actually forbidden lines. Forbidden lines because they only can happen in the low density of space. And these lines are not seen on Earth conditions. So after that, when physics was more developed, quantum physics in the 20s, and then people started to know more about this. It's also, you can link it to the difference between fluorescence and phosphorescence. Okay, just the last bit, which is actually the main, the main part, but very briefly, citizen science is something that actually I try to push for, something close to my heart. And what can amateur astronomers do? Say, why I buy this spectrograph and then what can I do with it? So there are a lot of programs and organizations that help us make use of our data. The fact is that there are just not enough telescopes. So there is still work can be done, useful work can be done by amateur astronomers. Ours is this, the Europeans are actually the leaders in this field. You see, they developed the instrument. The Americans, AVSO, they are really experts in light curves, but they have been quite slow to pick up on spectroscopy. GRAMMA is an initiative that they call it multi-wavelength, or was it multi-messenger astronomy, because it's with gravitational waves. When they have a detection, they send out alerts to us, people who are registered, and then try to get most of it is photometric, not spectroscopic, because they go to magnitudes of 16, 17. Okay. And yep, supernova. When I was in Hong Kong with some of my colleagues, I showed them, that night we observed supernova and recorded the magnitude and sent it to them. My friends thought it was quite cool, so we contribute to the light curve of the monitoring of supernova. Monitoring classical nova or variable stars. This is actually, this was actually a thing last year when I just came to Singapore. This is a project for HST, Hubble telescope as well. Why I show that? Because I thought it's quite exciting. With the AVSO, the pros, every few times in a year, they have a request to AVSO for amateurs to monitor in preparation for Hubble Space Telescope's observations. So they want to know whether this variable star is going into its dim stage. The irony is that it cannot be too bright, you will damage the equipment on Hubble. So they use amateurs monitoring to do work like that. So you actually contribute. And people who actually contribute a significant amount of data actually get listed in the paper as a co-author as well. And the last slide is just me showing off, because at this time, 2021, there was a nova in a telegram, and a newly discovered classical nova. And then that night, it was clear, and I stayed up the night to pick up a very early stage of the nova, which is this one. You can see the P Cygni profile, which shows a very high velocity, about 1,500 kilometers per second, expanding circumstellar gas. So when you do that and then you submit the spectrum, after that, when they finally put out the alert, and then my name was listed there, so I was very happy. And then a week later, that's how the nova has evolved to this. This is typical spectrum of a nova. I think that's about it. Kept to my time. Thanks a lot. Thank you very much.
So thank you, Mr. Tan and Mr. Seng, so much for both of your talks. So right now we will move on to the Kahoot quiz before we have the final Q&A segment. So, so while we wait for you guys to either type, I think I can start with the first question. So I have a few questions actually. Oh, okay. I think I will ask it's something related to the Kahoot quiz. So I will ask Hang, which is just now there was the question, what was the final stage like for the
Oh, I'm still there. It's just that my camera kind of malfunctioned. But no worries. Yeah, I can go ahead.
okay. So like you said that the iron is the last stage, right? So
Yeah.
that will be for the high mass stars.
Yes.
So can we say that carbon is the final stage for the low mass stars?
I guess you can put it that way, but the other way I'll put it is basically for low mass stars of 8 and below, one of the so-called finer element or heavier element that can produce is carbon. Yeah. So in a sense, yeah, I guess.
But usually when like they refer to final stage, it's always like the actual final stage that a star can possibly get to, right? Which is like iron.
But the production of iron requires really a more massive core. Yeah. So for low mass stars, they just don't have. And I recall if I recall correctly, I read somewhere for these low mass stars, by the time they reach the so-called the giant phase, the red giant phase, so that's where they are like kind of dying. They really have lost in a sense, lost the ability to produce more helium in their now mostly helium core, and they actually puff out right in the red giant phase. And if that process right, they actually lose some material as well. So as a result of that, right, so for this low mass stars, I think they simply just won't be able to go through more nuclear fusion. Right? Yeah.
Yeah, if I can
Yeah,
say something,
please.
is that's why there's a lot of CO white dwarfs and not so many helium white dwarfs. And then the ONE, the oxygen neon white dwarfs, are also rarer because you need a higher mass. Whereas one solar mass star in the red giant phase, they can after the helium flash, they can start to fuse some helium into CO. That's why when they die, they shed the outer layers. The white dwarf that is left is a CO white dwarf, which is quite common.
So I think we have some questions for you from the chat. So the first question by Rinaldi is spectroscopy used to find planets also? As I heard that they see how long a star gets covered by the planet. Also transit.
Yeah, that's a good question. Transit, usually there are a few methods to discover exoplanets. Have you done any exoplanet observation? It's done by photometry. You monitor the light curve of the star, and then when there's a transit, you see a dip, and it's amazing how much information you can get from the dip, the slope of the dip, the width of the dip, the time duration of the dip, and then you analyze this and you get some parameters of the exoplanet system. Other methods include micro lensing. What else? So radial velocity. Yeah. So there are a few methods, but spectroscopy is not really used to discover or find exoplanets. But it is a very high res. So spectroscopy is used to study the atmosphere of exoplanets. But but if you say radial velocity, then yes, it's one of the methods because radial velocity is from spectroscopy. I'm not sure now what is the percentage of discovery of exoplanet, which method is how many percent. I think microlensing is increasing. I can't remember the percentage. We'll have to find out on that.
We have another question for you by Yu Yang, which is, what creates the sodium line in the spectroscopy of stars?
Yeah, that's a very good question because I normally ask them, you see the Fraunhofer line, and it's this dark sodium line in the middle in the yellow. There must be a lot of sodium in the sun, right? If the sodium line is so dark. And so
most of us will probably know it's actually less than 1%, 0.0 something percent of sodium. And yet there is this dark absorption line of sodium in the spectrum of the star. And this is explained, it's a little bit like energetic UV radiation is blocked, or the far UV, which is the more energetic one, they can't pass through our atmosphere. Yet radio waves with low energy can pass through atmosphere and reach us. We can do radio astronomy on the surface of Earth. So it's not about how strong the energy, how energetic the radiation is. So this is actually a very good introduction to quantum physics, because it's about the discrete energy levels. The radiation must have the correct amount of energy to cause the transition, electronic transition. Otherwise, the electron just cannot. It's not a continuous spectrum for the transitions to happen. The electrons can only from here come to here, and then if you don't have energy to come here, it just stays here. You have too much energy, then it goes to the next level. But between the next two levels, it cannot be anywhere in between. It can only in this. So this is how I introduce some ideas of physics to the public or to my children or their friends. So it is a very very relevant question.
So that means like how bright the line is in the spectrum doesn't really translate to how much of the element there is in the star.
Yes, you can say that. That's right. Because if you compare the G star of the sun, or the A star, there's sodium, but the sodium amount is very very little. But the caveat to the answer is that studying the absorption waves and all that in depth does give some information about the metallicity of the star, which is the content of the star. So that's why when to do metallicity studies is very high resolution, then you can do. At 20,000 is a little bit, there's too much error in it. So you can actually study the line depths and the line width, how the waves actually evolve as the amount of element changes, and the temperature that causes the different amount of ionization and energy changes.
Okay. Do we have any more questions? Okay, then I will ask another question to Mr. Seng, which is, you mentioned about blue shift. So how does red and blue shift affect your data? And does the software kind of try to cancel them out?
Yeah. Yeah. Again, it's a very good question. Yes. Depending on what software you use. To give you an example to what you just asked, is that I've been measuring. I wanted to show you, but it's so cloudy to find this radial velocity of this star Canopus, the second brightest star in the sky. It has a radial velocity of about 21 kilometers per second moving away from us. So what I do is I take the line at H alpha 6562, and this 6562 compared to the rest wavelength on Earth, you see this little bit of redshift of 20 kilometers per second. But the Earth is also moving around the sun. So you also need to take into account that, otherwise you lose some accuracy. So at different, you sync your clock accurately, and then if you use the software that can do what we call heliocentric correction, the heliocentric correction will give you the usually -6, -5, -3, depending on time of the year, time of the night, and then it will give you this correction. So yes, you do need to take into account these different corrections. And the standard usually is called the barycentric, which is the center of mass of the solar system. That is the reference that most data uses. The slight difference from heliocentric, because the sun itself moves a little bit also. But the difference between the two is very small. But I find it quite cool to be able to measure redshifts of galaxy. And these are just amateur equipment and it's not a difficult exercise.
So beside you is your setup.
Yeah, yeah. Because I thought since Jihang made us stay at home, sorry Jihang, and then the advantage is that I use my astronomy PC to do the Zoom. But then it's so cloudy, you cannot see anything. I thought I'll just show you some live spectra, but unfortunately we can't do it tonight.
You could roughly show us your setup.
Oh, sure. Can you see? Is it too dark? My screen is. Oh, okay. So, this is usually for outreach. I use the low resolution because the low resolution gives you the coverage of the optical range, whereas the high resolution, this device actually the coverage is very small, just about 200 angstroms. That's why it's high resolution, and the light comes in, gets through the slit of at the moment I have a 35 micron slit is inside, and on the slit is actually a mirror. The mirror is for the guiding, as you saw earlier in the slide, and then after the slit it goes through the another mirror to reflect for the into the diffraction grating. For this high resolution, I'm using a 2400 lines per millimeter grating, and then it gets reflected back to the collimator and an objective lens into the camera. So that is the setup. The low resolution equipment is much simpler and easier to use as well, less demanding. By the way, we are very open. We are outreach nature. So anytime if anybody is interested to see real stellar spectra, just let me know or let Jihan know. I'm happy to show anybody.
Yep.
I think I'll ask another question to Jihang, which is I think about the HR diagram.
Yes.
So this diagram is like one of the most important diagram in like explaining stellar types and evolution.
Yes.
So I would think that our members might want to know a bit more.
Okay, let's see if I can bring it up again. Yes, here. Okay. Sorry, a bit like just anyhow. Okay, so oh wait. Okay, I hope y'all can see clearly because sometimes over Zoom might be a bit blur. But so earlier we mentioned about this diagram and how the x-axis and y-axis are plotted. Okay, the y-axis being the luminosity or like to represent the energy that the sun gives out, and the x-axis being the called brightness, which not say brightness, sorry, the sort of color, but it's actually more accurately the temperature, surface temperature that's being measured. So what scientists did is that they basically got a lot of stars measured, and then they kind of realized that those stars that are in the so-called phase where they are stably burning their hydrogen and the core into helium. Okay, those are called the main sequence stars. So you can imagine that they are they went through puberty and now like adults and stuff. Then depending on their initial mass, right? For example, if let's say you're a very heavy massive star like Sirius, you'll be on more left side of the main sequence sorry, the more on the more left side of the main sequence region, right? Because you're more massive, you burn a lot more faster, you burn with a lot of energy. That's why you are on the a lot of the higher side of the main sequence. Okay, and also you're hotter, that's why you're also on the left side as well, right? So higher, more energy, and on the left side also higher temperature. Okay, whereas let's say if like our sun, which is considered like an average star, and it's the less massive one, then you get something more towards the right side, the cooler, less energy given out. And then what scientists realize, or like astronomers realize, is that basically there are these stars that they are dying. Okay, and depending on where they are, they can usually move in a sense towards the top right direction. Okay, and also depending on the nuclear reaction that's going on, which also again heavily depend on the initial mass. Okay, they will either branch out to these giants, okay, or rather just in general the lower mass would be the giants or the red giants. Okay, and then for the so-called heavier, more massive stars, they will branch out or move towards, right, the supergiants. Okay, and then you see there's this column on the region on the bottom left. This is the white dwarf. So yes, they represent the white dwarf, right? Basically the remnants, all right, of the low mass stars that have, in a sense, died off. So you can imagine that, like, say for example, again our sun over here, all right, it'll sort of go into the giant's phase or red giant phase when it's old and it's dying, and you just branch here, and then after that you actually sort of go in a loop, right, back to this way as it goes through the final stage of its death, becoming a planetary nebula, leaving a white core behind. I think one of my diagrams earlier did have this pathway. Is it? Yeah, something like this, right? So the sun would be like this. Yeah. And then, of course, you can see the pathway of the so-called massive star. They will end somewhere in the supergiants, and then they will just end off in a supernova. Yeah. So this is also quite important because basically to kind of validate scientists kind of validate that their theory is kind of correct. One way is they actually use star clusters. So I'm not too sure if, oops, sorry, that's wrong. Okay, and okay, so the sun clusters. Oh, okay. Oh wait, I think Mr. Sun has something, but I think that.
Oh, sorry, am I?
Oh, I think you need, or because you typed to me, you want to type
Oh,
into
sorry,
the
wrong
chat, right?
message. Oh, sorry,
Yeah,
sorry.
about the sodium in the sun's photosphere. Yeah, like where do we have sodium in the sun? Also because our sun is actually a second generation star. Yeah. Yes. So back to this. Where was I? Yeah, correct. So one way to kind of like validate, like we kind of have a good idea of how these stars evolve. It's actually through the observation of star clusters. So we have these deep sky objects in the night sky called star clusters. As the name suggests, they're just clusters of stars, mainly two types, globular and open. So for the globular star clusters, right, they are usually a lot older stars, usually generation 1 stars, where they are in a sense low metallicity, right? Just low in matter. So in a sense, they are like early generation stars where they haven't gone through enough of the fusion to produce heavier elements. And also the open star clusters, which is quite interesting because they tend to have young, hotter stars, right? So you can imagine, let's say, a star clusters of maybe a lot of these massive stars, right? Some of them, which are more massive, will die earlier. So when scientists look at these star clusters, right, they will have a good idea that, you know what, they are born from the same molecular cloud, right? They should be born around the same time, right? So those that are more massive, they'll die earlier. They will actually be in the so-called supergiant phase, right? Or they will have already branched out, okay, towards the right side of the supergiant region, okay, and then we'll kind of again plot this HR diagram to just have a good idea of, like what is the stage of this star cluster, and whether it kind of validate their theory on how stars evolve as well. Yeah, so there's like one significant part of the HR diagram which I am able to remember for now, but there are a lot more other things that we can also remember as well. Okay, really sorry because my camera kind of stopped working, so I am not in frame except my share screen. Sorry, I talk a lot, like okay, all right, so I guess I'll stop share screen here if it's okay.
Yeah, Mirabelle is right. The HR diagram is very important and useful. Every time I learn about a new type of star, I try to place it and see where is it in the HR diagram. It helps you to visualize at which phase it is. But sometimes it's not so clear cut because in astronomy, a lot of areas have a lot of uncertainties. Sometimes we don't know, the errors in the distance measurements are huge. A lot of stars, we don't have very good measurements. Sometimes we don't know whether the star is evolving left or right, like the canopus that I just mentioned just now, I'm pointing at. It's somewhere right at the top middle, but so far it's still not certain. It's an F02, I think, supergiant. So it's not certain whether it's evolving to the left or evolving to the right. So that's the fun of astronomy. I think there's a lot of research, a lot of peer-reviewed papers. After you publish, your peers come up and counter-propose another interpretation of the data. And big data is also coming in a lot to astronomy as well. So it's very exciting. And gravitational wave astronomy as well.
So this diagram is like a mapping of the stars in our night sky.
Yeah, it helps me a lot. I use it as a map, like what you say. So, like when I first learned about Wolf Riot, then slowly you realize they have to be at the upper left, somewhere upper left or middle. And then you learn about the white dwarf, and white dwarf has to be, it loops from the top down to the bottom again.
I think another question that some people might have about the HR diagram is like, there are like four regions in the HR diagram. So does it mean like in the other spaces there are no such stars?
Not necessary, right? It's just that it happens that, like most of the supergiants will cluster in this region, giants will this region and main sequence. But like earlier, Seng showed, right, there's some like the so-called anomalies, then they have their so-called own clusters. But whether does it fill the whole, that I'm not sure.
Yeah, that's a good question. Then the question is, why are there gaps? The other point might be whether it's observable. But that's a good question. Interesting.
Yeah. I mean, maybe one day someone will find a different class of stars, right?
The fact that the HR diagram exists at all is precisely because of your question, Mirabel, I think, because when they didn't know about HR diagram, and then they started to plot the data. They plot the data, and then this 0H, this main sequence line starts to come out. And then they realize that there is some constraint from the physics of stellar evolution that places stars along these certain lines or areas. So I think that probably answers your question a little bit. That makes sense. But that's a good question. A very, I think it's a very relevant question. Good point. But it validates the physics. That's interesting.
So do we have any more questions from our audience?
Does the audience feels, I'm not sure how is it talking about amateur spectroscopy? Does it bore too many people, or do members of astronomy club find it interesting or exciting? Is there any chance of getting some feedback? I wonder.
I think maybe it can be a slightly too advanced. Yeah. Because because not all of our members are from science faculty, so they might not understand some of the content.
I see what Renadi is saying. Yeah, that's what I'm hoping for. Is it that it can be technical, but it's so interesting, but you want to find out more, and it's the same for me. So there's so much that I don't know. There's so much I want to find out, and it's technical. It takes effort. It takes time to find out. But I don't know whether, but because this we are talking about Astro Club. So, but for the public, then it's I found it very difficult so far.
I think sometimes the more challenging the content is, it makes you want to like understand it even more.
I'm still amazed by how much information we can find out from Starlight. It really amazes me.
So if there are no more questions, move on to this part. So this is the Instagram page of Science Center Singapore, and you can follow at this Instagram handle. And then we have the Facebook page of the Science Center Observatory. So both of them, they always have a lot of events throughout the years. And then if you are looking for more astro events, you should follow the Science Center Observatory Facebook page.
Thank you, Mirabel.
Okay, so thank you both, Mr. Sung and Mr. Tan, so much for today's talk. It's been very eye-opening to, especially being introduced to an area that most of us don't really think about and don't really have the opportunity to actually learn about. And also, stellar types and evolution is, I believe, is one of the most important topics in astronomy, and it's very important that our members learn about it. So thank you so much.